Hello everyone. This is the question 22 from IOQM 2023. We are given an equilateral triangle of side length 6. Pegs are placed at the vertices and also evenly along sides, each side at a distance of 1 from each other. 4 distinct pegs are chosen from the 15 interior pegs on the sides, that is, the chosen ones are not vertices of the triangle. And each peg is joined to the respective opposite vertex by a line segment. If n denotes the number of ways we can choose the pegs such that the drawn line segment divides the interior of the triangle into exactly 9 regions, find the sum of the squares of the digits of n. So this sounds like a very confusing problem, but let us first draw the diagram and see what it means. So basically we are given an equilateral triangle. So let us first draw an equilateral triangle. So this is not an equilateral, but assume it is an equilateral triangle, and pegs are placed at the vertices and also evenly along each side at a distance of 1 from each other. So what we do, we place a peg here, 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 suppose here, 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 and here. So basically total side length is 6. Let me try to draw it a bit evenly. So suppose peg here, peg here, peg here, peg here, and peg here. So pegs are distributed in such a way, and similarly on each side, like pegs are drawn like this. So what we are given such a triangle, and 4 distinct pegs are chosen from the 15 interior pegs. So from the interior pegs, we choose 4 distinct pegs. So how can we choose 4 distinct pegs? Either all 4 of them could be on the same side. So let us write that as 4. Or suppose we choose 3 from one side and one other peg from some other side. So 3 plus 1. Or what we can do is we can choose 2 from one side and 2 from the second side. So 2 plus 2. Or we can choose 2 plus 1, which basically means choose 2 pegs from one side and 1 from each of the other sides. Or yeah, this is the total number of ways of choosing 4 pegs. And okay, we choose 4 pegs. So suppose for example we go with say this 3 plus 1. So what we do, we choose 3 pegs from one side. Suppose we choose this and this, and 1 from some other side. Say we choose this, and so the pegs are chosen. And each peg is joined. Each peg is joined to the respective opposite vertex by line segment. So what we do, we join the chosen pegs to the opposite peg by line segment. Yeah, so something like this, and like this, like this. Yeah. So something like this is done, and we are asked to find exactly 9 regions. Notice that in such a case, if we choose the 3 plus 1 setup, there are a total of 8 regions. So 9 regions are not there. So this will not count as a configuration. We need to count. So let us first find out how can we generate exactly 9 regions. So let's go case wise. Suppose we choose 4 pegs from the same side. So if we choose 4 pegs from the same side, it is pretty obvious that the total number of regions will be, if we choose 4 pegs like this, the total number of regions would be 5. So it cannot be 9. So this case is neglected. In this case, 3 plus 1 is already cancelled. Let us find out what happens for the case of 2 plus 2. So in the case of 2 plus 2, we choose, say we select this side, we choose 2 pegs here and 2 pegs here. If we join it opposite line, notice that total number of region comes up to be 9. So this is one of the acceptable case. 2 plus 2 is an acceptable case. So first let us count the total number of ways of doing 2 plus 2, which is basically what are the total number of ways of choosing two pegs from two different sides. So first we need to choose the two different sides. So total there are three sides, and to choose two of them there are two ways. There are three ways. Three choose two ways, and from each side there are five C2 ways of choosing two pegs. So basically, in the first step we choose two sides. Then from each side, out of five we choose two. So 3C2 into 5C2 into 5C2. These are the total number of ways. If you count them, 3 into 5C2 is 10. 3 into 10 into 10. This comes out to be 300. So there are total of 300 ways in this 2 plus 2 case. Now let's do the 2 plus 1 case. So 2 plus 1 case looks basically like we choose two pegs from one side and one peg from each of the other side. So if we draw such a diagram, it looks something like this. Suppose we choose these two, and suppose we choose this one, and we choose, say we choose this one. Yeah. So what is the total number of regions? If we count the total number of regions, 5, 6, 7, 8, 9, 10. So total number of region comes out to be 10. But this is the only the general case. Suppose something like this happens, that suppose in one of the settings, three lines coincide with each other, something like this. In such a case, one of the regions gets deleted, and if one of the regions gets deleted, we are left with exactly 9 regions. So we need to consider this case when three lines are concurrent in the 2 plus 1 case. So what we are basically left to solve is we need to calculate the total number of ways in which 2 plus 1 can occur such that three lines are concurrent. So first let us count how can we make three lines concurrent. So at this point of time, suppose three lines are concurrent. Suppose this line, um, no, suppose this line, this line, and this line are concurrent. Yeah, you can prove that these three lines are concurrent. How? So basically, because the total side length is 6, and you should remember of Ceva's theorem. If you don't know Ceva's theorem, Ceva's theorem says that suppose we label the points as suppose we label them as A, B, C, D, E, F. It says that if BF by FA into AE by EC into CD by DB equals to 1, then these three lines are concurrent. So notice that here this is 4, this is 2, this is 2, this is 4, this is 3, this is 3. Notice that this ratio comes out to be 1, this product, and hence these three lines are concurrent. So basically, to count it, the number of concurrent triples of lines, we basically what we do to count the total number of cases, what we do, we calculate the total number of uh, three concurrent lines, and then we draw one other line. So we take suppose AD, BE, and CF, and we take suppose one other line anywhere. So this would count up to total of 1, 2, 3, 4, 5, 6, 7, 8, 9 regions. So this is what happens. So to count the total number of ways, we count the total second case 2. This is case 1, suppose. Case 2, the procedure is count the total number of three concurrent lines, and suppose we have counted a case, and notice that three pegs are already chosen, And out of the remaining 12 pegs, we need to choose one of them. Basically, 3 are chosen, and we can choose any one of them, and it would produce 9 regions. So there are total 12 ways of choosing one extra peg. And suppose we did this, suppose say this is equal to suppose S, then our answer in case 2 is 12 into S, because we can choose one other peg in 12 ways. So now the problem is left to finding the total number of concurrent lines. So to count that, notice that what could be the ratio. Suppose we check the ratio BF by FA. BF by FA could only be 1 by 5 or 2 by 4 or 3 by 3 or 4 by 2 or 5 by 1, or yeah, this is the case. So 1 by 5 corresponds to this point, 2 by 6 corresponds, 2 by 4 corresponds to this point, 3 by 3 to this point, 4 by 2 to this point, and 5 by 1 to this point. So BF by FA could only be one of these following. And similarly, let us write down BF by FA. We found out that it could be 1 by 5 or 1 by 2. 2 by 4 is basically 1 by 2, or 1 or 2 or 5. So this is the possible values of BF by FA. And similarly, A, AE by EC. AE by EC could be also the same set, and AE by EC is also the same set. And notice that CD by DB, CD by DB by using the Ceva's theorem is equal to FA by BF into EC by AE. So basically we use this fact and take these two terms on the opposite side. So this relation we get, and notice that CD by DB also belongs to this set. So we need to multiply these two numbers, and notice that FA by BF and EC by AE, these two also belongs to this set, because reciprocals, they are reciprocals of these two, and basically if you reciprocate this whole set, you will get this same set back. And so basically we need to multiply two elements of this set to get another element of the same set. We multiply these two elements and we get the third element of the same set. And notice that if you calculate the total number of ways of multiplying two elements of this set, you can do it manually also. You will notice that there are a total of 2 plus 2 plus 5 plus 2 plus 2 ways. So this is total 13 ways. How do we get this? Suppose we try to calculate how many numbers can we multiply with 1 by 5 to get an element of this set. So 1 by 5 we can multiply with 1 or 5 to get back an element of the same set. Similarly, 1 by 2 we can multiply with either 1 or 2. So 2 cases plus 2 cases. 1 we can multiply with any of the 5 elements. So total 5 cases. And 2 we can multiply with either 1 by 2 or 1. And 5 we can multiply with either 1 by 5 or 1. So total, this is the total sum of number of cases we get. And this comes out to be 13. So total there are 13 ways to get concurrent lines. And as calculated earlier, this is equal to S. This is equal to this same S. And total in case 2, the total number of numbers are 12 into 13, which is equal to 156. So in case 2, we get 156. And total we add up case 1 and 2, we will get 300 plus 156, which is equal to 456. So we are asked to find the sum of the square of digits, which is equal to 16 plus 25 plus 36, and this comes out to be 77. So 77 is the answer to our problem. Thanks.